So what we're going to be doing is generally, we're going to take one sample from a population, and our interest is in estimating a population proportion. And so what we do to estimate a population proportion that we generally don't know, just think about one proportion is, do you plan to vote for Joe Biden in the upcoming election? And it's a binomial, right? Yes, I do, or no, I don't. And the actual election day next Tuesday is when we'll find out what the actual result is. But until the election next Tuesday, the best we can do to estimate the percentage that will vote for Joe Biden is to take a sample from the population. And that sample doesn't have to be very large, you know, on the order of, 500 to 1,000. So let's just say it's 1,000 people, and actually call these folks up. You may have been getting these calls already. You'll see these calls and you'll answer them. You don't know who it is, and they're taking a poll. CNN, Fox News, Wall Street Journal, all of these different organizations, the Gallup organization, the Pew people, the Pew polls, Rasmussen, there's all kinds of reputable ones, and they're all calling right now to try to get a sense of how people are going to vote in this next election. But their samples are based on, 1,000 or less generally. And it turns out, as you'll see, that all that's required is about 1,000 to get a very accurate poll most of the time. And so the best we can do is to calculate one sample proportion from here. And we just take the number who say yes divided by the total in the sample. So yes, I plan to vote for Joe Biden divided by the 1,000. And that gives us a proportion that we can then convert to a percentage. And so usually when they do polling, they're going to say, oh, 52% in the recent polls said that they would vote for Joe Biden. So they do report this one result, but what they don't report is that it's based on a confidence interval, and we have to be very careful about how we interpret polls. All right, so that's kind of the backdrop. We're going to be calculating this sample proportion over and over again, and that one number is called the point estimate. If there was a single number that we could use to estimate a population proportion, it would be what we got from the sample, our one sample that we took. And that's called the point estimate. And in this section, since we're estimating population proportions, the point estimate is the sample proportion. Now, a confidence interval uses this point estimate, but instead of using only the point estimate, which is right in the middle, they add a little bit and subtract a little bit to create this interval. And this little bit that they're adding here is called the margin of error. So you may have heard that term before. So sometimes when they report these polls and they see a difference between Joe Biden and Donald Trump's percentage, they will say that either it's within the margin of error or it's outside the margin of error. And so you have an interval of numbers that is formed by adding the margin of error to the sample proportion and subtracting the same margin of error. And then you've got this interval of numbers. You can report it as a graph, as I've done there, or you can report it as an interval. So it's this interval that's called the confidence interval. It's a subset of the real number line. And what we're going to say, because we really know that if we take one p hat, we know that those p hats vary. And every time we take a new random sample, we're going to get a slightly different sample proportion. They'll all be very similar. And from the work that we did back in chapter 8, we know that if this is the true population proportion right there, this is the thing we're trying to estimate. When we take a single sample, It's very unlikely that we would land right directly on the population proportion because these things vary. In fact, we know that if we graphed many of these p-hats, you would see these p-hats all over the place. But they're all within about two standard deviations of the mean, sometimes a little bit less. And if we graphed all of these and did sample after sample after sample, we would fit this normal sampling distribution. So when we do one sample, we don't know if we've gotten this one or if we've gotten this one out here. Most of the time, we will grab a population, we will sample and get a population proportion closer to the sample proportion close to the population proportion, but not always. So you got to be very humble and vague in your language. We never use the word that, oh, and this proves that that Joe Biden's going to get 52% of the vote. And a single sample never proves anything. It just provides evidence to suggest that Joe Biden is likely to win. So we're going to look at we're going to get into the weeds a little bit here and look at how you actually construct these. And then I'm going to give you a calculator function that'll calculate this interval for you. But you need to understand the parts. And so that's where we're headed. Since we know that p hat is approximately normal if n times p times q is larger than or equal to 10, we know this. And so we must check this every time as well. We need to make sure that the sample size is large enough. And if that's the case, then we know that we're dealing in a normal sampling distribution. This was from section 8.1. Now let me just kind of review all the z values, all the z scores we have. In a sample with a mean, the z-score for a particular data value is equal to the data value minus the sample mean divided by the sample standard deviation. You saw that z-score. Or if the context was in a population, then we used that data value minus the population mean divided by the population standard deviation. We calculated z-scores in that context as well. Then we moved ahead to the sample mean. Oops. Maybe I'll just do a single sample over here. The sample mean. The z-score for a sample mean is equal to that mean minus the mean of the sampling distribution for the sample mean divided by the standard deviation of the sample. We'll call that the standard error of the sample proportion. And we also had a couple of formulas for these. For example, the mean of the means was equal to the mean of the population, and then the standard error of the sample mean was equal to the population standard deviation divided by the square root of n. And so we could actually write this new formula as, our sample mean minus the mean of the means, which is just the mean of the population, divided by the standard error, which is this. We'll come back to this one in the later sections, because right now we're focused on the sample proportion. And the z-score for a sample proportion, we take that sample proportion and we subtract the mean of the sample proportions divided by the standard deviation of the sample proportions. There was another z-score. But we also have formulas for the mean of the sample mean, that's the population proportion, and the standard deviation of the p-hats. And that was given by pq over n. So we can then rewrite this formula as p hat minus p divided by the standard error term, which is the square root of pq over n. And in case you forgot, q is 1 minus p. All right, so it is this z-score here that is the focus of this section, because it deals with sample proportions and then the sampling distribution of the sample proportion. But we know how z-scores work. We know what they mean. tells us the number of standard deviations away from the mean. All right, so I'm going to eventually bring this one in. And before I go and derive the confidence interval formula, I want to take you back to a problem that we've done in the past. And that is, what are the z-scores that mark the middle 95% of the data in the z distribution? So what is this z value and what is this z value? We'll call this one the upper one and this one the lower one. I'm going to ask you in the group work to replicate this over and over and over again. Okay, Chris, I got your email. Yeah, hotel internet's not that great. All right, so we know how to do this. You were probably asked to do this in some form or another on the midterm exam. If 95% of the data fall in the middle of the z distribution, then we have 5% that falls on the outside. So there's 2.5% in the right tail, and there's 2.5% in the left tail. 2.5, 2.5, and 95 all add up to 100, all the area under the curve. And so if we wanted to do this one here, the left area equals 0.025. The decimal, that corresponds to 2.5%. And if we wanted to figure out this z-score, then the left area is equal to, well, you've got to, from this point over, you've got to add the 95, and then you've got to add the 2.5. So it's 0.975 in reference to this. I should say the left area of that number. Now, some other terminology, we called this number right here z of 0.025. So we're going to come back to that notation. And we've used it in the past, and we're going to use it again. And you may recall that the calculator function that we use to calculate this z-score is inverse norm. And you need to give the left area of that z value. All right, left area is 0.025. And if we're dealing with the z distribution, the mean is 0 and the standard deviation is 1. So 0 and 1 would come next. And this upper one would be inverse norm of 0.975 and 0 and 1. All right, on the group worksheet, I'm going to ask you to come up with these z values for different percentages. It's a problem that you've done before, but these are important because these z values turn out to be what we call critical values. Now, you should not be surprised by these numbers. You've seen them before. We know as an estimate from the empirical rule that 95% of all the outcomes fall within 2 standard deviations. So 0, 1, 2 is about there. -1, -2 is about right there. So if we go 2 standard deviations to the left and 2 standard deviations to the right, the empirical rule says 95% of all the outcomes will fall within 2 standard deviations. Well, it turns out that the empirical rule was an estimate, as you saw. It's not really -2 and 2, it's -1.96, which is very close to -2, and +1.96. So these are the critical values. So if I refer to that, take yourself back to this picture, and you can generate it as you did in those problems back in chapter 7. All right, now we already know how to estimate a population proportion with a point estimate. The next thing we're going to do is we're going to estimate the population proportion with an interval, and that requires that we somehow figure out a formula to figure out what the upper and lower endpoints to our confidence interval would be. So what I'm going to do now is I'm going to derive the formula of how we find the margin of error. And I'm going to use this picture right here. And I'm going to write it as a probability statement. Here's what we know. That if you tried to calculate the probability of that z, which is our standard normal variable, some z value, is between negative 1.96 and positive 1.96. This is like saying, you know, what percentage of the outcomes fall between -2 and 2. In a normal distribution, and z is normal, it's in fact the standard normal, this is going to be equal to 95%, and we'll write it as 0.95. So this is what we know based on this picture right here, that the probability that z is between this number and this number is 95%. Here's how we would write it symbolically. All right, so for my, and the goal, just think of the big picture here. What I'm trying to do is to find the margin of error, because we need it in order to calculate the confidence interval. The first thing I'm going to do is I'm going to replace z with something that's equivalent to z in this setting. And so here's the z value, and here's the formula for the z value. So if we're dealing with a sample proportion, that z value right there is p hat minus p divided by the standard error term right there. Now, all of this that I'm about to do is all algebra. But in the end, we're going to have our formula for the margin of error. So what we're trying to do is to estimate P, the population proportion. And here is that P right here. That is the population proportion. So we want to try to estimate what it is. So I'm just going to go through this, and I'll let you look at this a little bit later. I'm going to kind of go quickly through the algebra, but it should look somewhat familiar to you. So the first thing I'm going to do is I'm going to put in our formula. Z is equal to, here's the Z score for a sample proportion. I'm going to do all the algebra inside the parentheses here. So the first thing I'm going to do is to multiply all three parts by this denominator, and that'll get rid of the fraction. So negative 1.96 times the square root of PQ over N is less than or equal to P hat minus P, less than or equal to 1.96 times that same fraction. So this is a property of equations. Whatever you do to, or inequalities, in fact, whatever you do to one side, you have to do to all sides. And the next step in algebra is we're going to subtract P hat everywhere. All right, so minus P hat minus 1.960 times the square root of PQ over N is less than or equal to negative P is less than or equal to negative P hat again plus 1.96 square root of P Q over N. And that's equal to 0.95. Now I have negative P in the middle, and I want to say something about P. So I'm going to multiply the entire inequality by -1. It changes the signs of everything. Not only that, it changes the inequality symbols. So I'm going to multiply these by a negative. Both will be positive. That'll be positive. That one's positive, that one's negative, but the inequalities are going to switch. So I'm going to bring this one over here, and it's going to be P hat minus 1.96 PQ over N, less than or equal to p less than or equal to, and then multiply this one by -1 and bring it over here, p hat plus 1.96 square root of pq over n. Now, we are where we need to be, because this says that the probability that the population proportion, which is what we're trying to estimate, is between these two numbers is equal to 0.95. There's a 95% chance that the population proportion is somewhere between these two numbers. These two numbers give us an interval. In the lower part of the interval, we have p hat minus 1.96 square root of pq over n. And on the upper bound, we have p hat plus 1.96 times the standard error term. And here is our confidence interval. It gives us an interval of values, and we know that there's a 95% chance, because of the way that this was constructed, that the population proportion would be in there. It's either, the population proportion is either in there or not in there, right? But if we looked at all these different sample proportions and did the same calculation, 95 out of 100 of them will capture the true population proportion, and 5% of them would not be very good estimates because they do not capture the population proportion. Most of them do. So if you compare this to p hat minus the margin of error that I wrote at the beginning and p hat plus the margin of error, then you can see that the margin of error is equal to 1.96 times this standard error term. Now, when we calculate this by hand, normally, if you look at this, it begins, both sides begins p hat, and then you subtract something, and over here you're doing the same thing, but you're adding that same something. So a lot of times what we'll do when we're calculating it by hand is just to worry about the plus or minus sign at the end and just calculate this. All right, the 1.96 that we wrote up here was due to the fact that we were interested in a 95% probability. If we were only interested in a 90% chance, then these numbers would change. Or if we wanted this to be 68, for example, the probability that z is between what two numbers is 68? Well, we know from the empirical rule it's about 1, -1 and 1. So this number is going to change as these numbers change, or these numbers are going to change as this level here. This level right here is called the confidence level, and we're going to call it C. C is the confidence level, or the C level, or something abbreviated like that. But the confidence level will change depending upon, you know, the researcher and the context and so on. So we want to be able to use this process for any confidence level. And when we change the confidence level, we are going to change these numbers here called the critical values. So we need to be able to find the critical values in a lot of different settings for a lot of different C's. All right. So the first thing I want to do to kind of stop, I've been talking for quite some time here, is to let you go into groups and work through a worksheet here. And this kind of sets the foundation for everything we do with confidence intervals, not only in this section, but you're going to see confidence intervals come back over and over and over again. So the problem that we just did was this one here on your worksheet. Find the two z-scores that mark the middle 95% of the area. So we did this and this. We said this is 95% and shaded all that. And we found that this one was negative 1.960 and this one was positive 1.960. And so what I'd like you to do on this worksheet is to do the same problem for all of these other ones. And I think I've included most of the popular confidence levels. So this one would be C equals 0.95. This one would be C equals 0.90. This one would be C equals 0.80. There's different confidence levels, those C values, depending upon how confident you want to be that you've captured the true population proportion. All right, now, once you get these Z values, these critical values identified, I want you to fill out this table down here. So I'm going to show you how to calculate the table. We did 0.95, so I'm going to come over here, and another value that you're going to see is alpha, and alpha is equal to 1 minus C. But in our row here, the C value is equal to 0.95. So 1 minus 0.95, this means that alpha is equal to 0.05. Now we have to split that in two to get the right area. The outside area, if the inside area is 0.95, the outside area is 0.05. If we take and just are interested in the left area or the right area, here it's asking for the right area, we take alpha divided by 2. Now alpha was what we just calculated here. So the alpha is 0.05. And we divide by 2, so we get 0.025. So the right area, and you can see here, the right area is equal to 0.025. The symbol that we're going to use is Z of that same alpha over 2. Notice alpha over 2 is now the subscript of our Z. So this is Z of 0.025. And then the critical value is the number that we calculated here, the 1.96. And we're always going to report the positive one. All right, so I'd like you to go through the rest of these. You can see there's a row for 80, 90, 96, 98, 99, and here they all are. So first come up and figure out what these critical values are, and then go complete the table. And that's what I'd like you to do. So let me give you the, let's see here. I'll give you the index document and then the link to it, and then we'll put you into groups. And we'll take about a half an hour for this. And I'll be monitoring to see what you find out. Of course, you won't be able to do much of the shading on the Google Doc. Okay, so there's the link. It should be there. Click on that to get the index document. And then I'm going to assign you into groups. All right, we'll do 3 groups today. There'll be 3 to 4 of you in a group. Again, turn on your camera, turn on your voice. Choose the person who's going to type into the document. Okay, welcome back. Looked like you had a pretty good handle on that one. What's important here is when you do these calculations, you're always going to be asked for the critical values. So remember, the critical values are down here. These are the specific numbers. Here's the symbol that we use for them, but these are the actual numbers that we're going to replace into the confidence interval formula. So I think we have kind of all the beginning stuff that we need. So I'm going to go to the notes that are in. Okay, so this whole section is based on estimating a population proportion. So it's all about proportions. In the next section, 9.2, we're going to basically replicate everything that we're doing today with the mean, estimating a population mean. And so we talked about the point estimate. If there was a single number that you would use to estimate the population proportion, the best one that you would use is the one that you got from the data, and that is the sample proportion. So when they ask for a point estimate in this section, just calculate the sample proportion. The confidence interval uses the sample proportion, and it also has to come with a level of confidence. This level of confidence is what in our earlier problems we referred to as the C level, or the value of C. It's going to be just a small set of possible C levels, confidence levels, levels of significance. 95% is a popular one, 99% is a popular one, 90 is a popular one. But you should be able to go through the calculations for any confidence level. We will interpret these confidence levels as we do some problems. And here is a reminder that we need to check n times p times q and make sure that it's larger than 10. And here is the population proportion. This is our formula for the mean of the sampling distribution. And here's the same thing for, I'll usually write NPQ, square root. All right, so this is stuff that you can just read over after class. I'm going to go to some problems. All right, so when we interpret a confidence interval, I'm going to ask for, there's really three things that you need to state. And you're always going to be asked, oh, by the way, there's only one more exam in this class, and that's at the final exam. And it's going to cover everything that we've done up to this point, or starting at this point. And so take very good notes, because you can use these notes on the final exam. So interpreting a confidence interval. There's three things that you need to include when you interpret this, these confidence intervals. You're going to get an interval of numbers, and let's see here. If we just look at this example and pull out the information, a USA Today Gallup poll asked 1,006, that's our sample size, adult Americans, how much it would bother them to stay in a room on the 13th floor of a hotel. Interestingly, 13%. So this percentage is what we get from the sample of 1,006 people. So this would translate into our p hat being 0.13. That's what we got from the sample. The margin of error was 3 percentage points. And then the C level, all right, so the C level was 0.95, and the margin of error was 0.03, 3 percentage points. The margin of error is what we're going to refer to as E. So if we did a point estimate in this problem, the point estimate would be the sample proportion. And just from reading the problem, we see what that is, 0.13. An interval estimate, what they're really asking for when they ask for an interval estimate, they're asking for the confidence interval. Now we know how to construct a confidence interval. We have p hat in the middle of our interval, and then we're going to subtract the margin of error to get the lower bound, and we're going to add the margin of error to get the upper bound. We can write the confidence interval in the graphical form like this, or we can just write the confidence interval like this, as an interval of numbers the way we would in describing a solution set in a math problem. All right, they give us both of these numbers. They give us the p hat to be 0.13, and they give us the margin of error to be 0.03. That's the E value right here. So this distance right here is 0.03. We have p hat 0.13 right in the middle. Interesting, people don't want to stay on the 13th floor because of superstition. 13%. All right, so if you take 0.13 and you subtract the 0.03, you get 0.10. And if you take the 0.13 and add the margin of error, you get 0.16. So here is our confidence interval. All right, now we know the context. We know that this is estimating the percentage of people that prefer not to stay on the 13th floor of a hotel. But when we interpret a confidence interval, the general formulaic way is there's going to be three things. One would be to state the confidence level. Every confidence interval comes with a level. Do we want to be 95% confident that we've captured the true population proportion? Do you want to be 90%? Or are you going to require even more confidence and have 99% confident? But you have to state the confidence level, because all confidence intervals come with a different level. Number two is to describe in words the meaning or the population parameter that you are estimating. And number 3 is that you have to give the boundaries of your confidence interval, upper and lower boundary values. And you want to do this using an appropriate unit. All right, so let's do it for this example. All right, the confidence level for our example was 95. So here's how we're going to begin with the first part. We're going to say something like, we are 95% confident that. Now you want this whole thing to be just a single sentence, single statement to interpret this confidence interval. All right, the next thing is to describe the population parameter that you're estimating. So we are confident that, and the thing that we're estimating here is the proportion. And really you just go to the kind of where it was described in the problem, and what they ask is, would it bother them to stay on the 13th floor of a hotel? That's the proportion, and they interviewed Americans. The proportion of adult Americans that would be bothered to stay on the 13th floor of a hotel. All right, so that's describing there's going to be a population proportion in a lot of different settings, and this is kind of where most of the wording occurs. The proportion of adult Americans that would be bothered to stay on the 13th floor of a hotel. That describes the population parameter in context. And then finally, you want to state the boundaries. You have to interpret the confidence interval, so you have to use the 10 and the 16. So, is between 0.10 and 0.16, or between 10% and 16%. A lot of times using percentages is a better way to interpret a confidence interval. All right, so this is what would be expected when you interpret a confidence interval in context. Say it all together. We are 95% confident that the proportion of adult Americans that would be bothered to stay on the 13th floor of a hotel is between 0.10 and 0.16, or between 10% and 16%. We have absolutely no confidence at all in 0.13. It's most likely that the population proportion is not 0.13, even though that's what we got from the sample, because we know that all of these samples, they vary. They vary dramatically. And so the chances that we landed perfectly on the correct population proportion is almost zero. Almost impossible to hit the population proportion exactly. However, if we take one of these, here's the 0.13, let's say, and we add a little bit and we subtract a little bit, this interval did capture the true population proportion. The true population proportion is in this interval. That's what we're after. All right, we can go and answer the question now that you know the formula. Which of these most closely relates to what we wrote down? What do you think? Go ahead and put your answer in the chat. Which one most likely relates to what we've done? Yeah, pretty much, I agree. You have selected A. A is pretty much exactly what we wrote down. But so get in the habit of writing that. We don't want to say that, you don't want to state a range on the proportion, as it doesn't say anything about whether 13, the chance that 13 is. We know that almost certainly 13% is not the population proportion because it's based on a single sample. So you don't want to state a probabilistic range. So part B is wrong. Again, the 0.10 and the 0.16 is all based on that one sample. So we don't want to talk about the likelihood that it's correct for that one sample. And we don't want to put a percentage related to 13%, part D. We are either we're probably 100% confident that 13% is not the proportion. So you don't want to say anything about the individual sample proportion. So the only one that works is this one here. All right, let's work through a couple of problems. We'll start with the simpler ones, and then we will move to some of the applications which are more interesting. Okay, determine the point estimate of the population proportion and the margin of error and the number of individuals in the sample with the specified characteristic X for the sample size provided. Okay, now I'll do number 11 and then I'll ask you to do number 12. So for number 11, they gave us enough information to create the confidence interval. And they told us that the upper bound was 0.249 and the lower bound was 0.201. They also tell us that the sample size is, so when you're constructing your confidence interval, you can draw a little graph like this. Now, they're asking for what is the sample proportion that you got from your study and what is the margin of error. So to figure this out, here's what we know about a confidence interval for a sample, for a population proportion. Lower bound, upper bound, right in the middle of this interval is our p hat. So you have to figure out, how to find that number in the middle if you know the endpoints. Well, it turns out that the number right in the middle is the midpoint, and we know how to calculate the midpoint. You take the endpoints and add them together and divide by 2. It's like taking the average of those two endpoints, and that's going to put you right in the middle. Also, we know that the margin of error is the distance from that middle point out to one of the boundaries. It's the same on both sides. All right, so let's first calculate what the sample proportion must have been by using this midpoint formula. 0.201 plus 0.249, add those together, divide by 2, and you get 0.225. And then there's lots of different ways that you can calculate the margin of error, but one way, if you know this number here is 0.225, then you could take 0.225 and subtract 0.201, or you could take 0.249 and subtract 0.225, or you could take 0.249 and subtract 0.201, but then that would be 2 margin of errors, so then you'd have to divide by 2. So there's lots of different ways to calculate the margin of error. In every one of these, you'll come up with the same number, 0.024. Okay, the last thing that they wanted you to calculate here is the number of individuals in the sample with the specified characteristic X. So they want the sample proportion, the margin of error, and then we're going to calculate what X is. How many individuals out of the 1,006 actually said, yeah, well, if it was our earlier example, it bothers me to stay on the 13th floor, or whatever our X is here. There's no context given to this one. But you use this formula. We've been able to deduce what the p hat is. So I'm going to put p hat as 0.225. We know the sample size is 1,006, so we can figure out the X by multiplying both sides by 1,006. All right, so the 0.225 is probably a rounded number. So what we're going to do, X has to be a whole number. So it's probably X is equal to 226.
Could you repeat where the 1,006 came from?
Yeah, it came up here from this other problem.
Okay.
Sorry about that.
Thank you.
All right, so this should be 1,200, right? I don't think anything else matters here. Yeah, so this is 1,200. All right, so let's do that instead. 0.225 times 1,200. 270. And it turns out to be a whole number, so 270. All right, and you can confirm that if you take 270 and divide by 1200, you get the 225.
Can you do the X value, please?
Sure. We do know that in this example, n is equal to 1120, and you calculated the p hat to be 0.0625. So what we're going to use is the sample proportion formula, and we're going to plug in the two numbers we do know, and then use algebra to find the missing x.
I used the 0.0115 instead of the 0.0625.
Okay.
That was my error.
Now I would like to go and calculate a confidence interval using our confidence interval formula. And the confidence interval formula is, if you recall, we have p hat minus the margin of error, which is the z critical value. We used 1.96 in our first example, times the standard error term, p q over n. That's the lower bound, and then the upper bound is p hat plus the margin of error. And the z of alpha over 2 is the critical value that I asked you to calculate earlier, times. And when we usually do these by hand, and maybe I'll do number 16, usually we just write a plus or minus z of alpha over 2. Okay, there's one other thing that I have to share with you, and that is that we don't know what the population proportion is. That's why we're trying to estimate it. So where it says PQ over N here, this really is the population proportion and 1 minus the population proportion, but we don't know those numbers. So we're going to use the best thing that we have to estimate it. And the best thing that we have to estimate the population proportion is the sample proportion. So our formula is going to change a little bit so that P hat is going to go here and it's going to go here. And Q hat, as before, is 1 minus P hat. All right, let's take a look at number 16. The first thing we have to calculate is P hat. P hat is X over N. They give us the X, they give us the N. We can punch that into our calculator or do it in our head, however you want to do it, to get the sample proportion is 0.4. So we have 0.4 plus or minus. Now we have to go find this critical value. It's the critical value that corresponds to an 80% or 98% confidence interval. If 98% of the area is on the inside, then 2% of the area is on the outside. So if you take 2% and divide it by 2, you get 1%. 1% is in the left tail. And here's where you're going to use these numbers from your table. You see 98% confidence interval here, and you just scroll over till you get the critical value in the far column. So it's 2.326. That's why I had you calculate all these. These are the most common confidence intervals. And here's another one, 2.326. So this is the critical value that we're going to call Z sub 0.01. So Z of 0.01 is 2.326. We're going to bring that number over. 2.326. All of these numbers are going to be close to 2, 1.96, 2.326, 2.054, 1.645, and so on. Then we multiply by the 0.4 times the 0.6. Okay, so Q hat is equal to 1 minus P hat. And these two numbers are always going to add up to 1. And then we divide by the sample size, which is 200. All right, so I'm going to punch these in on the calculator. We have 0.4. I'll do the minus first. Minus 2.326 times square root of 0.4 times 0.6 divided by 200. And that is 0.31942. I'll round to 5 decimal places. Now, really, I shouldn't round to 5 decimal places. Really, I should only round to 3 because our critical value here was rounded to 3. So I'm just going to get rid of those last two. Now, all I have to do is to go back and change that minus sign to a plus sign, and I'm going to get the upper bound. 0.48057. I'm just going to round it to 3 decimal places and put a 4 there. Construct a confidence interval of the population proportion at the given level of significance. Now, if we calculated a 95% confidence interval here, the interval would be different. Okay, now before we go into the applications, I now want to share with you the calculator function that we're going to use in this section. So just about everything, every calculation that we do from now to the end of the class will involve the test menu of the stat menu. So let's go to stat. That's where we've always been going. Edit, still there if we want to edit or enter in our data or sort it, so on. We can calculate some things here, but where we're going to spend the second half of this course is over here in this test menu. And the calculator function that we're asking for that will calculate this confidence interval for us right here. Well, it's about a proportion. It's about a proportion. It's just one proportion. The sampling distribution is the Z distribution. And we're going to calculate a confidence interval. So we want a single proportion. Z distribution is the sampling distribution. And then we want to calculate a confidence interval. So look for this function. A lot of them are the same. Notice number 5, it's similar, but it's not what we want because this one ends with the word test. And we want the one that ends with the INT for interval. You can see Z interval here, so that's a confidence interval. If you scroll down further, you'll see T interval. This is what we're going to be using in section 9.2. And then you have these ints or tests. So everything is either a confidence interval or we're going to look at, beginning in chapter 10, we're going to be looking at hypothesis tests. And that's why you see test at the end here. But the one you want is option A, 1 prop Z int. These are set up as menus. So all you have to do when you come in here is to identify the numbers that you have to specify here. And notice it always asks for the X and the N. So the X in our problem was 80 and the N was 200. So 80 and 200. And then the C level was 0.98. If you had a different confidence level, the calculator would give you a different confidence interval. And then come down and calculate. So this is 80. X is the frequency, so it must be a whole number. A lot of times students, when they're learning this for the first time, they'll type in the population proportion in place of the X. So if I happen to do that here and just type in the 0.4, because maybe that's all that was given in the problem, you can see the calculator is not going to like that at all. There's an error. So we really do need the 80. All right, and we'll come down. All right, and so N is 200. That's the sample size. And then we have the C level. And use a decimal instead of the percent. And that's the C that we've referred to in the C level. All right, so when you calculate, remember it's calculating this, but it's also going to give you the sample proportion, the p hat. So here it is. It gives us the interval, 0.319, 0.481. If we wanted 5 decimal places, our calculation up here, we could have given 5 decimal places. They give you the p hat, and then they give you back the sample size. All right, let's take a look at number 26. Now we're going to get into some applications. And the good news about these problems is that we have that one prop z int, so whenever we need to calculate the confidence interval, we don't have to go through all of this. You're going to have the calculator whenever you need it, so you really don't need to go through all of this stuff here. We're going to go right to the calculator function. Saving for retirement. Retirement survey of, all right, so this is number 26. From the stem of the problem, we can pick out the sample size, 1153. All right, and these are workers and retirees in the US 25 years of age or older. It was conducted by Employee Benefit Research Institute in January of 2010, and it found that 496. These are the number out of the 1153 that had less than $10,000 in savings. Certainly we would expect younger people not to have many savings, but if they're retired, then we would expect that by the time retirement comes along, they've built up a big enough nest egg so that they can live comfortably in retirement. That's not always the case. Many people live paycheck to paycheck and have zero savings by the time they retire, and then all they do when in retirement is to try to live on Social Security. And most individuals who live only on Social Security are very, very close to the poverty line. Okay. We have all the information that we need. There's no mention of a confidence level up here, so let's go on to the parts. Part A, obtain a point estimate. Now the point estimate is the p hat. We take one sample and we find p hat is always given by this formula. We take the two numbers that they've given us in the problem, divide them out, and we'll round this to, maybe the nearest, 3 decimal places, or 3 up. Part B says verify the requirements for constructing a confidence interval about P are satisfied. So this is the one where we have NPQ must be larger than or equal to 10. If NPQ is larger than 10, then we have a normal sampling distribution of P hat. And we don't know P and Q, so we're going to use the next best thing, N P hat Q hat. All right, we just calculated in part A that P hat was equal to 0.43. So it follows from there that Q hat is 1 minus P hat. And that would be 0.570. Our N is the same N in the original problem, 1153. So let's plug the numbers in. 1153 is N times P, 0.430 times Q, 0.570. Usually with a sample size larger than 1,000, you'll meet this requirement. But let's confirm. You'll see that it's going to be much larger than the required 10. All right, check. It has to be a random sample also. Everything that we do from here to the rest of the course requires a random sample. If you don't have a random sample, then we can't conclude anything. We can just report our results and just say that it's descriptive statistics. But we can't infer to the larger population. Now, retirees in the United States, there's a lot of them. There's millions and millions. So we don't have to worry about this criteria that N has to be less than 5% of the population size. It's satisfied. All right, so C, I'm not going to go ahead and use the formula on this. Rather, I'm going to go ahead and use the calculator function. So for C, the C level is 0.95. It's the first time we've encountered what the confidence level is. And so we're going to use one prop z int. We need x, and that was given to us up here, 496. We also need n, that's the 1153. And then we need the sea level, which is our 0.95. We already know, because we calculated it by hand, that rounded to 3 decimal places, the sample proportion is 0.430. All right. We're going to ask the calculator to calculate the sample proportion for us. We're also going to ask the calculator to give us the interval. So stat, and then go over to the tests menu. And all of the problems in this section, 9.1, you're going to be using the one prop z int. Type in the numbers, the inputs that are required, and then calculate. You can see there's the p hat, there's the n, and then we're going to write down the interval. 0.402, and I'll round it to 3 decimal places, and 0.459. Construct the 95% confidence interval. They say construct, but the construction of the confidence interval requires these calculations. So here's the answer to C. And then D says to interpret. All right, so we're going to make sure that when we interpret the confidence interval, we're going to write the one statement that's required. And we're going to specify the 3 things. You need to state the confidence level. You need to describe the population parameter that you're estimating in words. And then finally use these 2 endpoints. So we'll say something like this. We are, the first part of it is always the same. We are confidence level % confident, or I am that. All right, so now comes the description in writing of what we're trying to estimate. That the proportion of workers and retirees. A lot of times what you do is just kind of go up to the problem, and wherever they define the variable up there, you use that language. In the US, 25 years of age or older that have less than $10,000 in savings. Okay, so this is the middle part, the longest part. Okay, we're confident that, and now we have to use the intervals. Is between 0.402 and 0.459, or between 40.2% and 45.9%. So we're not very confident in the point estimate, the 0.430. That was determined just by some random sampling variation. We do suspect that it's fairly close to the population proportion. What we're very confident of, 95% confident of, in fact, is that the true population proportion, that this interval captured the true population proportion. So it doesn't narrow it down completely. For example, we know that this entire interval is less than 50%. So we could say that, we're fairly confident that less than a majority have $10,000 in savings. But we have to be very vague and not be too confident, not be too sure in our results, because they're all based on one random sample. All right, there's one other thing that we need to talk about that is involved here. And this is, what if you wanted to manipulate how confident, manipulate the margin of error? What if you wanted to say, well, our previous problem, we were somewhere between 40% and 46%. And that's a 6% range. What if we wanted to have only a 4% range? If we had if we get it somewhere between 42% and let's see, 42% and 44%. What if we wanted to narrow it down much further? The only thing that we can do as the researchers to do this is to increase the sample size. So here are a couple of formulas here, very closely related, that tells us what our sample size should be so that we can achieve a margin of error that's to our liking, small enough. And this all comes from the margin of error formula. We know that the margin of error is equal to our critical value times p hat q hat over n. If we solve this one for n, then we'll get the formula that you see. So for example, I would divide both sides by the critical value and get this. Then I would square both sides. Squaring a square root just gets rid of the square root. Then I would take the reciprocal of both sides, and then I would multiply both sides by p hat q hat. And this here is the formula that you see right here. So it just uses algebra and solves the margin of error formula. This margin of error formula here, it solves it for n using algebra, and this is what it comes out to. So I'll usually write it p hat q hat instead of 1 minus p hat. But you can see z of alpha over 2 divided by the margin of error. All right, now in some cases, a previous p hat is known. They did a study early on and they found that p hat was equal to 0.3. In other problems, you're starting off fresh and you don't have any previous results. So we're going to use p hat from an earlier study if given. Otherwise, use p hat equal to 0.5. And the reason for that, and of course, if p hat is equal to 0.5, then q hat is 1 minus 0.5, which is also 0.5. And then p hat times q hat is 0.5 times 0.5, which is 0.25. And the reason for that is that in order to, if you're looking for a sample size and you don't know what p hat is, what will give you the largest sample size is if you choose p hat to be 0.5, because if you choose p hat to be 0.5, then p hat q hat will be the largest possible value, 0.25. I can show you just kind of to give you an intuitive sense of this. P hat times q hat is in our formula. So we're not interested in p hat alone, we're interested in the product. What is going to make this product the largest that it possibly needs to be? And so if you just take different values of p hat, and I'm just going to take the possible p hats up to 1. Well, so if you just let p be all this range of possible p hats, then you subtract each of those from 1, then q hat would be 0.9, 0.8, and so on, like that. And then if you multiply these two, 0.1 times 0.9 is 0.09, 0.2 times 0.8 is 0.16, 0.21, 0.24, 0.25, and then when you go up here, it goes back down to 0.24, 0.21, 0.16, and 0.09. So you can see the largest value of this product, p hat q hat, is equal to p.25, and that occurs when p hat is equal to 0.5 and q hat is equal to 0.5. All right, let's go put this into practice in a problem. So here you can see n is equal to p hat q hat times this fraction squared. In this one, you can see the fraction squared is still there, but they've used p hat q hat to be the largest that it would be, 0.25. And the other important thing is that we're always going to round up to the next integer when we find this n that we're looking for. All right, here's an example. This is number 38. Credit card. A school administrator is concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of college students who have credit card debt of more than $2,000. What sample size? So when it says what sample size, you want to find n. And when you need to find n, you need to use one of these two formulas up here. If she wishes the estimate to be within 2.5 percentage points. So that is the margin of error. 2.5 percentage points. As a decimal, 0.025. We have the C level is 0.94. So what we have to do is to find the critical value. That's the Z. What is that? 94% in the middle. That means 6% in the tails combined. So if you divide that by 2, you're going to have 3% in each tail. So we're looking for Z of 0.03. We have to have it because the Z critical value is the numerator of this fraction. And is that in the other sheet? No, we don't have 0.94 here. So we're going to have to do the same work that we did here. If you put 0.94 in the middle, then the 1 minus C would be 0.06 divided by 2, and you get 0.03. So this is Z of 0.03, and then we're going to use the inverse norm to find it. 1.88, and I'll call it 1.881. All right, now we're ready. Now the two parts that you see here is that in the first one, they're saying that a pilot study indicate that the percentage is 34%. So what they're giving you is a previous study, and they found p hat to be 0.34. In which case, q hat, we need that, would be 1 minus 0.34, 0.66. If no prior estimates are used, then we're going to use p hat equals 0.5, which makes q hat 0.5, which means the product is 0.25. All right, I'm going to do the calculations up here because we have the formula. So in the first example, where we know p hat is 0.34 and we know q hat is 0.66, and then we take the critical value, this 1.881 number, and divide by the margin of error, which is the 0.025, and then we square that. And that gives us 1270.341325, and then round up. N has to be a whole number. It's a sample size. So N equals 1271. Even though if we rounded mathematically, we would actually round down to 1270. In this case, we want to make sure that we meet the confidence interval condition. And so you always have to round up. All right. Now, when you don't have a previous study and you must use 0.25, this formula is always going to yield something a little bit larger than the other formula because 0.25 is the largest product. So 0.25 times the same two numbers, 1.881 divided by 0.025, and we square that. And this one is typing it all in, 0.25 times 1.881 divided by 0.025, and we're going to square that number. And we're looking for something a little bit larger than 1271. 1415.2644. So 1416. I'm going to round up again. All right, so the answer to A is 1271, and the answer to B is 1416.